So we have seen process and threads. So we will see some more details of process and threads when we discuss the kernel in the kernel mod sessions. Now, kernel and user data structures. We have seen the user data structures, which are peb and teb. I would like to restrict my discussion with peb and teb here in this user mod internals part. And we will see a couple more important data structures like eProcess, kProcess, kthread, ethread, etc. when we discuss kernel. Peb and teb we have seen. Peb has the environment variables, loaded binaries, a lot of process-related, process-wide data structure connected to peb. And teb we have the stack base, stack limit, then a thread local storage, all those things are connected to teb. Now I wanted to discuss Win32 APIs and system calls. Most of the Win32 APIs are system calls. Not all of them are system calls, but most of them are system calls. I will take the example of a Windows API create file. Let's see how this particular API works, and we will see some of the system calls which is going into the kernel in a kernel debugger after that. So again, we have the address space here. This is the 4 GB address space, and the upper is user and lower is kernel. There is an application running in the upper. This is the application binary code which is loaded into the upper 2 GB. This is the application binary, so it has code. In one of the functions, we are calling the Win32 API create file. This could be any Win32 API which has a kernel switch like, create window, create thread, create process, anything pretty much. I'm just taking the example of create file. Create file, what it does is it creates a file object inside the kernel. Most of the APIs, what it does is it creates or manipulates some of the data structures or device states inside the kernel or on the device. So that is how most of the API works. In this case, create file creates a file object and it returns a handle to that file object. That is what it does. First, it takes the parameters, for example, the file name, the permissions, so on and so forth. With all that information, which is nothing but parameters passed to the create file, it calls ntCreateFile. There is always a ntdll equivalent, a native function, ntCreateFile. ntCreateFile is exported by the ntdll, just like the name. ntCreateFile, what it does is it creates a system call, or it creates an interrupt and switch into the kernel. The call is coming here and it switch into the kernel. That switch is caused by an interrupt, a software interrupt. That is called system call. Previously that interrupt was in2e, but now there is an instruction called syscall. So it's all same. It is a software interrupt. Remember what happens when an interrupt comes? The operating system switch into the kernel and the kernel can handle that interrupt. The interrupt service routine is always in the privileged mode inside the kernel. As part of the handling, couple of things operating system does is copying the parameters. Some of the parameters are copied from stack to stack. Some of the parameters are copied from registers. Depends on the number of arguments and the type of the arguments. Most of the thing it does is copy the arguments to the kernel. In the kernel doesn't trust the user mod. What it does is it verifies all the arguments. So what is being passed, every kind of all possible security level verifications are done on those arguments. Any possible problems, it just returns an error, the right error, and it continues. Now, if everything is fine, what it does is it creates the object which we are trying to create. If it is a file object, in this case, it's a file object. If it is a process, it'll create the process. Now, there are other functions which we can use to manipulate or use this object. For example, in the case of create file, it returns a handle. File object is created inside the kernel, and that file object of course points to a real file inside the file system inside the disk. That is a different story. What matters to us is a file object, a data structure inside the kernel, and there is a handle return. So there's a handle return. This is a handle return to the user mode. So handle is a number, a small number. It's not really a pointer, but it is a small number which points to this particular object. There is a handle table, etc. here to map inside the kernel. It returns a handle to the user mode. And using this handle, we can call other system calls like I was mentioning before. Write file, read file. If it is in the case of thread, create thread, then we can terminate thread, do any operations on that thread object using that handle. That is the general nature of Windows APIs. All the APIs works on data structures inside kernel. So some APIs are slightly different. So they work on user mode data structures. So get command line arguments. So command line argument, like I was mentioning, it is in the user mode. So it is in the PEB. Get command line argument doesn't switch into kernel. It just copies that command line argument from the PEB and it returns. There are a couple of APIs like that as well. But most of the APIs make a system call, switch into the kernel, create or edit the data structure inside the kernel based on the handle, or return a handle, or delete a particular data structure. So that is what it generally does. So now let's have a quick look at the kernel debugger and see a system call drilling all the way to the kernel from user mode. So it's a pretty common thing with almost all the threads. So I have a kernel debugger broken into a live kernel, which is a virtual machine in Oracle VirtualBox. What I'm going to do is I'm going to do a bang process 00. So this is a command to list down all the processes in the system. So I'm going to take a process. I'm going to stop this. I don't want this command to fully finish. I'm going to take a random process, say for example, winlogon. I'm going to execute the same command, bang process 017, then winlogon. So I'll explain all this command later when we discuss kernel. Let's see the system call. That is the purpose of this particular demo. What this command is doing is that it'll dump down that particular process, the winlogon.exe, and it'll show you all the call stack of all the thread inside that process from user mode to kernel mode. Let's see that. Let's take this particular thread. If you look at the child EPP or even the return address, so we can see that all these addresses still here is user mode. It is starting from 0, which means the most significant bit of this particular address is 0, which means that it is a user mode address. This is coming in the upper 2 GB. Now, if you look at this particular address, it starts with 8. Now, what that shows is that the most significant bit of this particular address is 1. That's why it is 8, which means that these are kernel mode address. Where is a switch happens? Right here. The function which calls or switch into the kernel is this particular function, k-fast system call ret. And that is the last function which is got executed from NTDLL. After that, the control is being taken by the kernel itself. NT is the kernel. It is running in that lower 2 GB. Now, if you look, you can see a trap frame here. This trap frame is a signal that there was an interrupt. Whenever there is an interrupt, you will have a trap frame. And you can do a dot trap to switch into that interrupt context. Now, as you can see, the thread is starting here. So this is where the thread start. Then it is executing some winlogon process related, application related code. Then it is executing some RPC related code and then further NTDLL. And it is calling this particular function. This is a function which is calling this and then switching into the kernel. Now what I'd like to show you is the instruction which is switching into the kernel, the syscall instruction. first what we have done is we have done a dot process, then the winlogon. This is a command we have executed to see the winlogon stack. So now what I'm going to do is I'm going to take the pointer of the winlogon. This is the winlogon pointer, or I can take it from here. So it's all the same thing. So I'm taking this pointer from here and executing the command dot process /r/p, then the process pointer. So what I'm doing is I'm switching the context of the debugger. I'm switching the debugger, not the operating system. So operating system is not executing anything. It's broken into the debugger. I'm switching the debugger context to this particular process. I'll explain all these commands later. Right now, I just wanted to focus on one particular function, which is this particular function. So this is a function which does the system call switch or system call or kernel switch, whatever it is. I'm going to do a UF. I'm not expecting much from UF. The reason why I'm not getting much from the UF is because there is optimization. The frame pointer is optimized, so UF is not able to understand the limits of the function. So I need to go a little bit up and down. Let's go a little up. What I'm going to do is I'm going to do a UB on this. So UB is giving me the stuff which I want. Let's see a bit more UB. L20. Yeah, this is what I'm interested in. So this is the instruction sysenter. This is the instruction which I'm interested in. So this is the instruction which is switching the control to kernel. This instruction will cause an interrupt, a software interrupt, and the control will switch into the kernel. And based on the interrupt, kernel will take whatever decision it needs to take to handle this particular interrupt. In this case, it'll copy the arguments and validate the arguments. Whatever the request is, it try to call the requested function for that particular API. Now, if you look at here, there is a corresponding call in kernel as well. So it is nt wait for single object. Pretty much it is the exact same code, just that there is validation of argument and further implementation call. So this is the actual implementation call. So this is a common practice in kernel when you do a syscall.